The first thing I was going to do was just give you this alternative formula for the dot product because it's really useful. So let me just remind you what the dot product between two vectors is. So you have a vector u, a vector v. There's an angle between them, and then the dot product is just the product of the lengths times the cosine of the angle between them. And then if you saw, I think I sent you that announcement on Monday. There's like a short like video about the dot product, which is kind of fun to watch. So like I'm kind of like created like kind of like an assignment. It's also called quiz, which is just kind of like 3 or 4 like multiple like short answer questions about the video. So the video I think is like 10-12 minutes long. So if you watch it, you can just answer those questions and but hopefully you see like you it might go so like mentions some of the applications of the dot product, so it's kind of nice to know just because of that. I think you still like kind of have the settings so that you can do unlimited attempts on the video, but like on the questions, but it is like you know very easy, just copying some numbers that like some appear I think towards the end of the video if I'm not mistaken, where they meant like he mentions like an application um involving dots and gaps or something like that. I know I don't remember too well. But yeah, just keep an eye on that. I mean from time to time I'll do something like that where I'll just find like a video and tell you to like answer 1 or 2 quick questions about it. Um so that's like one version to like this is one way to compute the dot product. Um and it has like many nice like it makes clear many properties of the dot product. For example, that is zero for perpendicular vectors and things like that. But it's also convenient to have a formula that work in terms of the coordinates of the vectors. So it's actually um, easy to derive. So the idea is like if you have 2 vectors, like let's say u and v, like again, I'll put u here. So it has like 3 entries, and I'll put v somewhere else. Okay, so you want like the formula for the dot product in terms of the entries of the vectors. So this is how we can do it. Let me show you how that works. Um, the key is kind of that's why I mentioned last time the unit vectors. The key is to actually rewrite the vectors in terms of I, J, and K. So U is just U1I plus U2J plus U3K. So let me write it this way. Okay, so that's what U is, and then you're taking the dot product with the other vector V. But V can also, again, be broken in terms of like the IJK vectors. So you put here V1I plus V2J plus V3K. Okay, so why do I do it like that? Because then what you want to do is take advantage of the distributive property of the dot product, which I mentioned last time. So once you set it up that way, you can say, okay, see, so if I use all the colors, it'll take me forever. So I'll just put it like organize it like this way. See how. So there's I can be dotted with this one, and this one. So you'll get U1, I. Oh, actually, what ends up happening is that you like something like U1, V1, I dot I. You get U1, V2, um, I dot J, plus U1, V3, I dot K. Oops, this should be a dot. Okay, then there is still, we're not done, right? So there are more things you can find here. And you can do like the stuff in the middle, the second one with these three. So you can U2 V1 J dot I plus U2 V2 J dot J plus U2 V3 J dot K. But by the way, no one, the idea is not that you would do this every single time. Like you'll see that there's a nice formula that will come out of this, and then there's a formula that you'll use. But I'm just kind of showing you where it comes from because it's a like it's a not a terrible derivation, so it's kind of nice to see what the idea behind it is. And then the last term is like U3V1 with K dot I plus U3V2 K dot J plus U3V3 K dot K. So it's actually 9 things that come out. In principle, actually simplifies a lot, but it looks like you just get 9 terms, okay? And I'm just kind of organizing them in a way that's kind of nice. Is that making sense how they appeared, 9 terms? Okay, so my claim is that actually 6 of them are automatically 0. That's the nice thing. So anyone could tell us who each is.
Like I dot I, J dot J, and K dot
So I dot J, so for example, I dot J and I dot K, they will be 0 because they're perpendicular. Yes, so like these two will be 0 because they're perpendicular. Then like, for example, J dot I, they're perpendicular vectors, so this goes away. Okay, this, like, so the ones that involve different vectors, they automatically become 0 because these are perpendicular. Is that making sense? And so the 9, only 3 remain, and then in fact they I kind of arranged it like for those who have seen matrices, it looks like a 3 by 3 matrix, so it's kind of cute way to present them. So it's actually not, I mean, there's another reason for doing it that way. But so they kind of like the ones that survive are these that you see along the diagonal, and then you are like say, well, it's just you just have to find I dot I, J dot J, and K dot K. If you remember from last time, the dot product of a vector with itself is its length squared, right? So we had seen last time that regardless of the vector that you have, for any vector, W dot W is the length square of W. So that's convenient because what happens here? Oh, these are unit vectors, right? So it's like kind of like 1 squared, like the length is 1 squared, but that's just 1. So it actually gives you 1, then you get 1 here, and then you get here 1 because length is 1. So what seemed like a big mess actually ends up simplifying like a lot. So let me give you the last the final formula. It's just like essentially if you look at the formula, like what you do is like multiply the first entries together, multiply the second entries together, multiply the third entries together, and then just add all of that. So I'll use it back in terms of the original color. Okay, so that is a formula for the dot product in terms of the entries, and this is the same as like the product of the lengths times the cosine. Okay, so they are like alternative ways of computing the same quantity. Okay. about to do some examples, but isn't making sense? So that's why I said, like, if you remember, like I mentioned last time, like, oh, there's kind of like a silly, but kind of like, like the first good attempt to try to multiply the vectors was kind of like maybe just multiply their entries and make a vector out of that, but that's not quite what works. You do multiply their entries, but then just add them together. That's kind of like the magic, but like it was not super obvious to, if you start with this formula, that's not super obvious why it kind of is so useful. But then if you start with a more like geometric definition, then like and then connect that with the algebra, with the formula in terms of algebra, then it kind of looks a bit more natural. So just to give you a quick example. Let's see. Okay, yeah, so if I gave you those two vectors, what's their dot product? So the idea is like, you kind of multiply them, like, if you write them this way, it's kind of like a vertical multiplication, so you do 2 times -1 plus 1 times 3 plus -1 times 1, okay? So let's see if that gives me 1. So it's -2 plus 3 minus 1. Oh, okay, so that gives you 0, right? And now we know that those vectors are perpendicular. So that's kind of like the idea of like how you play with the formula. So that means because their product was 0, so they must be. Remember, perpendicular are also orthogonal vectors. Another name for perpendicular is that they're orthogonal. Which just based on their entries, like, is not super obvious because you would have to try to draw that and then, make sure that like it's kind of like an accurate picture of it. So in fact, like just to show you, because again, I want to show you how to use GeoGebra. Fun of it. So and you can like plot them if you like. Oh yeah, this one is a manual one. Yeah, you can go to the 3D calculator and then you like make a vector, like you do like a point which is 2 minus 1, 1. We can check it in a second. -1. Okay, so I think one of the entries was incorrect, right? So,
1 minus 1.
okay, 2, 1 minus 1, thanks. So like, when you, oops. Uh, so what you can do on GeoGebra, just to get familiarized, once you enter the points, you can like type something like vector P, and that shows you draws for you the vector that goes from the origin to that point, which is the one that you see here. Let me see. And then you can also do the vector to the point Q. Okay. And then you kind of have to rotate like the picture in some way so that it kind of looks plausible that there are 90 degrees, which kind of seems okay. You can just like, yeah, if it's kind of fun to play with it, like the perspective. But yeah, there seems to be like 90-degree angle there. So it's kind of verified by the computation of the background. Um, that's kind of I'll have like that's kind of like the advantage of having like an alternative way to find it, because then you can play with both formulas for at your convenience. So like one of the one common way to use the two formulas at the same time is that it also gives you like a formula for the angle between two vectors. Just coming from here, coming from here, you can say that the cosine of the angle between two vectors is this. So now that you have, like now, for example, you can compute the numerator using something like this, and then you can find like the lengths very easily with Pythagoras theorem. So taking like arc cosine, that would give you like the actual value for the angle. So the fact that you have like the two formulas together is what it would allow you to now like find the angle between vectors if you know their entries, for example. Does that make sense? So that's like a common use of the dot product as well, to just like find angle between vectors. But for that to work, you really need like this alternative version, because otherwise it's kind of circular. Okay, so were you going to ask me? Good. Any questions before we move to topics? So yeah, for now, that's kind of what I wanted to say about the dot product. There's this thing called the vector projection, which I'll get to later, but it's kind of like it takes a little bit of time to just explain it, and it's not too important at this moment. So once we talk about lines, actually it's easier to explain. So for now, this is like the stuff about dot product that you need to know. So I can move to the next operation, which is the cross product. Okay, so that's the other way that we'll study to multiply vectors together. Well, let me erase this here. Okay. So this one is definitely more confusing than the one we just did. Let me try to explain what the idea is here. So this is what. So you have two vectors, right? I'm going to multiply them in a different way. So this is going to be called the cross product. So let me tell you what this is supposed to be like. So I'm going to do something that I'm going to call U cross V. Okay. And the idea here is that this is going to be a new vector. So before with the dot product, you got a number. Now you want the vector in this case. So this is going to be a new vector. Okay, and the key property of the cross product is that the vector that you produce is perpendicular to the original two vectors you started with. So for example, in this picture, like, if I have the vectors like this, if I have the vectors like this, like the cross product is going to be a vector that's perpendicular to each of these original vectors. So for in this case, it will look something like this. And I have to say a few more things about this because there may be a couple things which are not entirely obvious, but the important thing for now is that the cross product is a new vector perpendicular to the original ones, okay? So it's perpendicular, again, orthogonal to U and B. So the question, actually, the first question is like, in my picture, why am I choosing the vector that seems to be pointing towards like the ceiling instead of the one that's pointing towards the floor, right? Because if you think about it, if I have like the two vectors like this, then yeah, this one is clearly perpendicular to those two vectors, but you just turn it around and that continues to be perpendicular to those two vectors. There's still also like the discussion about the size, right? Which is even haven't told you, but like just in terms of direction, there seems to be like two natural choices for the direction, right? So that's where the right-hand rule comes in, which maybe some of you have seen before. So the direction is determined. So let me put it like this. There are two natural choices for the direction, and the direction is chosen using the right-hand rule. So in terms of direction, there are two choices. There are two choices, and we use the right-hand rule to determine the correct choice. There are two choices. To determine the direction, to choose choose the correct direction. Well, let me explain it like with those things first, and then I'll write what the right-hand rule says. There are a couple of rare ways to write it, but in terms of like how it works. Okay, let's think of U as the orange one and B is going to, so U is the smaller one in the picture, so U will still be the smaller one here in in what I'm showing you right now. So I'm trying to make U cross V, okay? So the right-hand rule says like, put your no, that's why it's called the right hand. Align your right hand, the fingers of your right hand with the vector U, okay? And then twist your fingers toward the vector V, and then your thumb will give you the direction of the cross product. So this is U and this is V, so I kind of want to close or twist my fingers towards V using the smaller angle, right? Like, because remember, there are always two angles between vectors, so just move it, use it, close your hand using the smaller angle. So in this case, for example, if I put my hand like this and I'm trying to close it towards V using the smaller angle, that's kind of why it seems to be pointing upwards. Like you need a little, again, like it takes a little bit more perspective on the board, but like, if you put them like this, it's more clear maybe. So that's like, and again, there are other ways to do the version of like the right-hand rule, but that's one way to do it. So you just place your right hand along you and close it towards V. Or close your finger and like move your fingers towards V, and then your thumb gives you the direction for the cross product. Okay. Um, Making sense so far, so good. So if you look at this rule, again, just going back to this example, to make U cross V, you know, I place my hand on the first factor. So I'm placing my right hand on the first factor. So it's kind of like important to think about how is whether this would be different or not from V cross U. So let's think about V cross U, what it should be. Again, like just thinking about it like from the concrete, um, with these concrete like pointers. So if I'm going to do V cross U, now I have to place my right hand on V, which is a longer vector here, and I have to close it, my hand towards U. But you cannot close it this way now because now you're closing it using like the bigger angle. The rule is kind of to always choose a smaller angle. So how can I close my hand towards U by choosing the smaller angle? I just have to, if you think about it for a while, you kind of have to change the direction of your hand, and now you can close it without problem. So like that makes the thumb point in the opposite direction. Okay, so what I'm trying to say is that in the picture, the other choice ends up being, the other natural vector that was perpendicular here actually ends up being V cross U. So. Is that making sense? Which gives you the conclusion that V cross U is minus U cross V because you just reverse the orientation, or you reverse the direction. So that's how you end up getting that, which is like a very important property of the cross product, the V cross U is minus U cross V. So meaning that if if you change the factors, you get a minus, like an overall sign. So in other words, like the order doesn't matter, but there's still like a relation between the two vectors, like, the two cross products. One different, like, they're just pointing the opposite directions. So, but this is a kind of like maybe the first example of a type of multiplication, where the order doesn't matter. In like, unless you have seen matrices, right? Which means like that's another case where like multiplication matters, the order matters. Is that making sense? So, that's how the direction gets determined. But remember, a vector is not only the direction, but also the magnitude. So the question also is, how do you want what do you want the magnitude to be for the cross product? Okay. So the like again, you'll see in a second that it's like a nice convention. So like the way you take the magnitude to be is to be the very similar to or like magnitude or length, sorry. So what's going to be the magnitude of the cross product and the length? So regardless of the order in which you take them, as U cross V or V cross U, they will have the same size. And the point of their lengths is that it will be the product of the lengths of U and V. So that starts looking similar to, you know, that kind of looks similar to like the formula for the dot product, how it started. But instead of using the cosine of the angle, now you just use the sine of the angle between them. Okay, so that is the formula for the length of the cross product. Uh, why, so why do you define it this way? Let's try to think about that. See. So the reason why you define it this way is because of the following fact. So why this formula for the magnitude? Okay, let me do the picture in a slightly different way so that it's a bit easier to see what is going to happen. So if you have two vectors, like I have mentioned this already a few times throughout the class, the course, like you can make a parallelogram with them. And you build a parallelogram, these two vectors, and then you can ask what's the area of the parallelogram, right? What is the area of the parallelogram? So if you remember, like the formula for the area of a parallelogram, that's base times height. Okay, so that's what I'm calling here, h. H represents the height. So it's just base times height. So what is the base here? I'm choosing the base to be just the length of the vector u. So this would be the length of the vector u. And what is the height? Well, so how can you find the height from this picture? If you call theta this angle, there's a right triangle here. You know, you can see that sine of theta is just h, right? Divided by the hypotenuse. And that gives you like the formula for h, which is just like the length of v times sine of theta. Right? Just multiply both sides by the length of v. So that's h. Or what is the length of u times the length of v times sine of theta? That's exactly the length of the cross product. So the cross product is the sine so that its length ends up giving you the area of parallelogram. Okay, so this is the length of u cross. So in other words, what I'm trying to say is that the length of the cross product is the area of the parallelogram of the vectors that you can build with the vectors u and v. Let me write that down. So here. So sorry, the length of u cross v is the area of the parallelogram with size u and v. So just a quick clarification, in case you like to think in terms of units, if you think about it in terms of units, units of area are kind of like feet, square feet, or like square miles, square meters. What but length is usually like in feet or miles. Um, meters. So what do I mean by saying that these two things are the same? I just mean that numerically they're the same. So for example, if the length of the cross product happens to be 10 feet, um, then the area of the parallelogram is 10 feet squared. Like, you know, that if you choose the same units, then the numbers that are in front of the units are the same. Because in math, we don't kind of will carry down the units, right? So I'm just saying like the actual numbers that you would see in front of like both quantities agree. So it's not that you're equating length with area, it's just you're just equating like the numbers in front of the units with each other. Okay? That making sense? So like it can be confusing if you know if you think about it in units. So like what like it's kind of like a what I'm trying to make is kind of like a numerical statement that the numbers that appear in front of those in the number in terms of in front of the area and the number in front of the length uh after followed by the units are the same. Okay, in practice, again, we don't worry about units, so it doesn't matter for us, but you know, it's kind of like an important thing to keep in mind. So, like, you know, there's like let me give you some examples of cross products. Uh, so like I mean by that I just mean like physical examples. So one the angular momentum. So like this is L, we just call angular momentum. So the idea there is like you know um you have like a particle with mass m at certain position um has a position vector with respect to the organ given by this position vector r, and the particle maybe has like some momentum. As a momentum, like if you haven't seen it, it's just like mass times velocity. So the angular momentum is just like what, like r cross p or something like that. So that's why sometimes we can actually show you how this works in a couple of weeks because it's a cute derivation. If you if you do the Kepler problem, like you have like the Earth orbiting the sun, it's easy to show that the angular momentum is conserved there. And that's why you get this Kepler's law that in equal times like the planet sweeps out the same area because angular momentum being a cross product is related to area. And that's kind of like you just have to do a little bit more work, but it's actually like it's like a very cute like argument that you can make. But for that, we need a little bit more uh, you know, information. So that's one example. And the torque is also another example of a cross product. If you have seen that before, if not, don't worry about it. Which is just like similar, but it's just like R, what's that? Something like that. Okay, so I'm just saying like the cross products like do come up. They're kind of like they're useful things to compute. And there are other examples of like cross products in physics. Yeah, there's like actually like I don't know who has seen like Veritasium videos. They're really cool. So there's like a very cute one with angular momentum. I'll like ask you to watch it because it's really fun. Kind of explains a lot of these things about the cross product. Very nice. So okay, and now I can explain. Now I can also kind of explain how I have been drawing my axes, like X, Y, Z, why I draw them in the way I do, because the convention is the following. So So when I draw X, Y, Z, why do I always draw it this way instead of like placing the axis in a different orientation? Because you have like the I vector, right? Here you have the J vector. And you have here the K vector, right? So the reason why you draw them this way is, so for example, that I cross J. Let's see, what should I cross J be? So think about it just to make your life easier. X is the axis that's pointing towards X is pointing towards you. So it's like the one that's leaving the board. So I have to put my right hand along the I vector. So imagine closing that towards the Y axis, which is this way. So what happens when you get I cross J, you get K, right? So the convention is to choose the axis in such a way that I cross J gives you K. Okay. And then from that, you can kind of figure out the others by like a similar argument. You know, if you do J cross K, you get I. And then if you do, if you do K cross I, let's see, let's let K cross I, so you get, no, I'm doing it is, what am I doing? I'm going to do K cross I, so yeah, is J, I think so. Actually, I'll give you a trick in a second to remember them because they can be tricky, except the first one, because it's kind of like alphabetical. So a nice way to remember these is that if you kind of draw them in on a circle, if you draw them on a circle, like say you move clockwise. So I cross J gives you K, then J cross K gives you I, and then K cross I gives you J. So, you know, when you move clockwise, like, and do the cross product following the order, the result is the third, the remaining one in that order. So it's like a, you know, it's like a cyclic order, what's called sometimes. So it's just like, that's an easier way to memorize them. But it's a good exercise to do it in your head, you know, like actually think about putting your physical hand along the vectors and convince yourself that it works that way. And the consent, so first. Okay, so before, again, and now we're headed in a very similar way to what we were doing with dot product. So with the dot product, I kind of started with a more geometric version of what it is, and then I gave you earlier today like a more algebraic version. So I want to get to the algebraic version of the cross product. That just requires a tiny detour into determinants like of matrices, and you'll see why, but like I'll explain what I mean by that in a second. Before doing that, let me just mention two more geometric things that are kind of useful to, you know, to have. So the first one is, what do you think? So here are like some other two other properties. So if you have a vector, what should be the cross product of that vector with itself? What?
Zero, because there's like no area in the.
Right, so one way to think about it is just in terms of the formula of the area of the parallelogram, or also the angle between them is zero and sine of zero is zero, right? So regardless of how you want to think about it, it's either you cannot make a parallelogram, right, without with area, or like just like in the formula for the length, you know, there's nothing like sine of zero is zero. So the cross product of a vector with itself is a zero vector. So that's like kind of completely opposite from, in a sense, like from the dot product, because when you then take the dot product of a vector with itself, it is like the length, right? So in general, it's always non-zero. Okay, this is a vector, but still, it's always like every entry vanishes. So in that sense, like that kind of like very extreme situations. And then more generally, like a generalization of this is that U cross V. I hate it when this happens. Oh, what? Okay. And I'm sure like it will turn out again in a few minutes. So U cross B, like the generalization of this is that this gives you the zero vector whenever U and B are parallel or anti-parallel. So whenever like the two vectors point in the same direction or opposite direction, because again, you cannot make the parallel, you cannot make like an interesting parallelogram in that situation whenever. Or parallel or anti-parallel. So because like here, like the angle theta is zero and sine of theta equals zero if you like. And here the angle theta is either zero or pi. And sine of zero is the same as sine of pi. So dot product is zero when the vectors are perpendicular, and cross product vanishes or is zero when the vectors are parallel, anti-parallel. So they kind of like work in different ways. So in us, like the rule of thumb is that if you want to check if two vectors are perpendicular, use the dot product. If you want to check if two vectors are parallel or not, use the cross product. Okay, so here's so the dot product has to do more with perpendicular things, right? So dot product to check if two vectors are perpendicular. Are perpendicular. And cross product to check if two vectors are parallel or anti-parallel, basically. Is that making sense? So just trying to compare and contrast them. And the other property before if we can find the formula for the cross, the other formula for the cross product is that it's nice to know that it still has a this distributive property. So just like well, this is like one property. Oops. Okay, so that's one property. And the other one is that if you have like, U cross V plus W. And this continues to work kind of like in the same way with the dot product. You can just like, do the separate multiplications. So you can do U with V and U with W. But the important thing here is like, since on the left-hand side, you got crosses, you have cross products. On the right-hand side, you need cross products as well. So you can still distribute. I mean, this is kind of like a property that's required for the cross product, if you like, if you think about it. So, And that's like, again, we'll play with this formula to find the distributive property is really like the one that does the trick if you want to find the algebraic formula for the cross product. But before that, let me just do like a quick example, which does show you that cross product, it does look like the formulas for cross product can look very different from like the regular formulas. But here's again an example, like just to show you that you have to be careful. So like, let's start with numbers or scalars, you know. If I have a numbers, scalars. Right, what is u minus v times u plus v? So what do you get? Right, you get like the difference of square formula. So like you get v squared minus v squared, right? That's with numbers, and then you can ask, well, what's a cross product version of? By the way, with dot product, it does work basically the same. So you can check it. I won't do it here because like my focus today is like cross product. But if you do u minus v, right, dot u plus v, you know, you distribute your FOIL, whatever, and then you get u dot u minus v dot v. Okay, so dot product and regular numbers for many formulas, they just kind of look almost identical, you know, like you can kind of make a good guess of what the formula is just based on what you know with numbers. But let's think about what the version of this is for cross product. So this, let's do it now with crosses here. So let's do u, so let's look at the formula for cross product. So let's do u minus v cross u plus v. Okay. So what does that give you? It gives you this one with this one, so you get u cross u. Then this one with this one, it gives you u cross v, right? Then this one with this one, right? That gives you minus v cross u. And then this one with this one gives you minus v cross v. That okay? Everyone with me? Is that making sense? So I distributed, right, like, and get 4 terms, right? But now, what's the difference in this case? What happens with these two cases? Like, they're like cross product of a vector with itself, they go away, right? Like the cross product of a vector with itself vanishes. So actually, the things that appear before now disappear, right? Because it kind of behaves like the opposite. So that's where you have to be extremely careful. So if you do that, you get u plus v, sorry, u cross v minus v cross u. And again, if you were in the regular world, these two will cancel, right? But now the order matters, right? So you cannot cancel them. So if you want to, you know, just kind of make it look the same, you know, you can change the order in one of them. So you can say, for example, we have said that v cross u is minus u cross v. So you get u cross v minus u cross v. So if you like, you can write the formula just 2 times u cross v. Okay, this matters less than just the fact that you cannot cancel it here. Like that's like another point that's important to emphasize. So it's kind of like in these two versions, like the u only goes with u and v only goes with v, right? And in the cross product version, like kind of like the what you would call the mixed term, uv goes together, and that's the one that survives. So in general, you know, if you like, my point of with this is that if you have like a regular formula that you know of, do not try to just like replace everything with crosses and think that it would work, because most likely it's kind of like the opposite of like, you know, what you know. For dot product, it's like a good guess to check. Oh, probably it would go that way, but you should still verify it. But for cross product, most likely just will be completely different. So that's what makes the cross product kind of fun, like those things, because it's kind of like you do have to rederive a lot of like identities, see how they look with cross products, things like that. Is that making sense? So far, so good. Okay, so now let me start moving towards like what I wanted to tell you, which is like what's the actual formula for the cross product in terms of like, the entries of the vectors. So now let's do the formula for the cross product. So let me do like a big version because that will give me an excuse to talk about matrices. So let's say that you have two vectors, U and V, but they're actually on the XY plane, meaning that their third entry is 0. Let me just draw them like this. So they're actually on the XY plane. So I could have just drawn them on the XY plane, but it's fine. Like I wanted to draw them in space. So the both vectors are like, it's kind of like if I had them on the desk. Okay. So I want to know what U cross V should be in this case. So what is U cross V? Then we do the same trick as the one I started with in today's class. Write it in terms of I and J. So you can write this as U1I plus U2J, right? There's nothing with K because like it's 0 times K. So you don't have, like, I'm just doing that to simplify my life. So there's nothing that involves J here. And then do the same with V1 and V2. So this is like V1I plus V2J. Is that okay? And kind of similar to what we just did for like this different of square formula, let's just distribute it. So you get something like, you get U1 V1 I cross I plus U1 V2 I cross J, and then U2 V1 J cross I, and then U2 V2 J cross J. Is that okay? And let me give you a second to copy this. So it looks like you have 4 terms, but they're actually less than 4, right? Because of the cancellations. So what cancels here? I cross I goes away, right? Because the cross product of a vector with itself is 0. So this one gives you 0. 0 vector, I mean. Same for J cross J, that just gives you 0. So that also goes away. And the others are easy, right? So what is I cross J? That's just K, right? So you have K there. And what is J cross I is minus K, right? Like it's the opposite order, so just negative K. That making sense? So what do you get? You get, so notice that these two terms have a K in common, so you can kind of factorize it. So you get U1 V2 minus, because of this minus sign, U2 V1 times K. Or if you prefer, let me rewrite it in a slightly different way. What I'm trying to say is that if you do V1, V2, comma 0 cross V1, V2, comma 0, you're getting K is 0, 0, 1. So you're getting 0, comma 0, comma this number. So you're getting V1, V2 minus V2, V1. Okay. So because this is like, case 0, 0, 1. So you just multiply the last entry by that quantity. And this, like, it looks a little bit fun, like odd, but that's what's called the determinant of. So that's what I'm about to explain you right now. So so this is like the correct formula, but you don't want to memorize it this way. Like, okay, so now in the last few minutes, I'll just tell you the basics of the determinant. And then Monday of next time, I kind of will just write what the formula is in the general case. So there's like this thing called matrices. So let's start with matrices. So this is like a small detour, but it's needed to understand a little bit better. So what is a 2x2 matrix? It's just an array of 4 numbers. I mean, there's actually a lot more you could say, but all that about this. So what is a 2x2 matrix? An array of 4 numbers. So for example, how is that usually written? Like it gets written like something like this. Like you write something like 1, 2, minus 1, 3, there's a matrix. Usually you use capital, like you capitalize the uppercase letters for like matrices. So this is a matrix, this is another one called the zero matrix actually. This is another one called the diagonal matrix. And you could keep going. Okay, so matrices, you just look like this, kind of like what you would put on a Excel spreadsheet or whatever. So it's kind of like a table with 2 rows and 2 columns. It's just that instead of like using like a table notation, you just put like this like round brackets around the numbers. Okay, so 2x2, like again, we don't need to get into many details of what this is, but 2x2 just means that there are 2 rows and there are 2 columns. Okay, for us, like we only need 2x2 and 3x3, so like there's not too much like to worry about how to read these things. So, and then the determinant of a matrix. Okay, so what's the determinant of a matrix? It's called that of A, so T of A. That's just a number. That's going to be a number. So actually, it is the area of the parallelogram that you get if you think of the, you can think of the. I'll show you how this works in a second. But if you think of the matrix A as being A, B, C, D, okay, then the determinant is essentially this weird combination that you see here. So the determinant of A is A times D minus B times C. I'm about to do a few examples here so that this idea sticks. But so like the idea is that you had four numbers, you multiply them in pairs, but you multiply them in pairs in a kind of funny way. You multiply like this diagonal, right? To multiply the elements on the other diagonal, and then you subtract them. So there's a difference of two products of the elements along the diagonals. Okay, so for example, let's just do it in these few cases. Like I'll just do it in doesn't make a lot of sense to do it for this one. But let me just do it in the other three cases so that you have some values, some numerical values. So if A is 1, 2, -1, 3, what is the determinant of A? So what I'm saying is that multiply the numbers along this diagonal, so that gives you 1 times 3, and then multiply the numbers along the other diagonal, that gives you 2 times -1. Okay, and then you subtract the values. So we get 3 minus 1, so this is actually -2, but with this minus because it's 2, so that gives you 5. So this minus is always coming from the formula. Okay, so this. So there's always a minus from the formula, and then you just like multiply the diagonal elements. And for example, D, let's just do D because also that's a little bit more interesting. If you take D there, like -1, 3, 7, 4. What's the determinant of D? Okay, you multiply the elements along this diagonal, so -1 times 4 gives you -4. And then again, there's a minus from the formula, and then 3 times 7 gives you 21. So that's -25. Is that making sense? So how I'm finding these numbers, so it's just like multiply the elements along the diagonal and if you multiply the elements along the diagonals and then subtract those answers. Oh, why am I telling you this right now? Because if you look at this formula, I think I'll probably just finish here because like the 3x3 case, just better start it next time. Once we discuss, like, and that way I can just give you the general formula both at the same time. So if you look at this formula, the idea is that if you had if you look at this formula, if you just ignore the last column because that column is just made out of a bunch of zeros, you have like a mini two, like you do have like a 2x2 matrix hidden here, right? So you could call it A, which is like U1, U2, V1, V2. In fact, let me use the same colors. And so the determinant of A would be is like U1, V2 minus U2, V1. And that's precisely what appeared in the cross product. Okay, so essentially my point is that the only reason why I'm doing this is because it is easier to give like re-explain the formula of the cross product in terms of determinants. So what I'll do next time is give you the formula for the determinant of a 3x3 matrix, and then it's very easy to write like the general formula for the cross product in terms of the determinant of a 3x3 matrix. That's kind of the point of doing it this way. So if like you don't need to go through determinants to find the formula, because in fact, like kind of we already were doing that. It's just like, when you put like a new U3 here and a B3 here, if you wanted to memorize what you get, it's a lot easier if you just like go make this detour about determinants first, then just kind of write a huge formula for it, because I can, in fact, let me just, before we finish, like, I think it's like, I can find it pretty quickly on Wikipedia or something like that. So if you know. Oops, just to finish with this. So what I'm trying to say is that okay, so yeah, like it's actually like like they just distribute like crazy. You can try it at home if you like. So you end up finding this formula. So I won't do this derivation again because it's exactly the same thing that I just did before, just a bit more terms. But just so you just find all these numbers multiplying ij and k. Like what I'm trying to say is that it is hard to memorize these numbers in these particular combinations, like how they appear. But if you just rewrite it in terms of a determinant, which is what we'll do here next time, then it's super easy to memorize. So it's kind of like this determinant thing is just like a good way to memorize the formula for the cross product. But to find it, like you just distribute like what we just did a few minutes ago. So next time, what I'll just tell you is like, how do you find the determinant of a 3x3 matrix and rewrite the cross product basically in some version like this, and then that's a nice way to keep it stored in your head. So yeah, I'll see you on Monday. So remember, like you have the presentation. Let me just in case someone else.